In this video, we are going to be talking about a couple of things that happen when we have reactions taking place in aqueous solution. And so we need to start by looking at solutions themselves. And if you recall from chapter 6, we know that when solutions form, it's because the solute particles are being evenly distributed throughout the solution. And we know that this happens because the interplay of the forces that exist between the solute particles in each other, the solvent particles in each other, are overcome by the intermolecular forces that exist between the solute and the solvent. And so we have a increase in attraction from solution making compared to when the solutions were on their own. And so pictorially, we saw this in chapter 6, the idea that in aqueous solution, especially for ionic compounds, what happens is that the water will actually start to separate the ions from each other. Now, why is this important? Why do we stop to look at this particular detail? Well, it's because if we're examining the concept of solutions from the perspective of ions, then we have to be sure that when we combine solutions together, we actually know that something happened. Because if I have a series of ions before that have all been separated by water molecules, and a series of ions after that have all been separated by water molecules, how do I actually know that anything changed as I combined the two solutions together? Now, luckily, chemical equations can give us a little bit of an indication to let us know if anything is happening when those two solutions are combined. And so what we're getting into are two primary types of chemical reactions. The first of which is going to be the primary focus of today, are the precipitation reactions. A secondary reaction is something called an acid-base reaction, and we'll talk a little bit about those today, but we'll really leave that up for future discussion on a later date. So let's look at precipitation reactions. Precipitation reactions are reactions that form a precipitate. That is a solid product that comes out of the reaction of two liquids, two solutions. Now, common example of this is the reaction between sodium chloride, NaCl, and silver nitrate, AgNO3. If I take these two solutions, which are both clear and colorless, and put them together, what I'll end up with is a white precipitate, silver chloride, and a colorless solution, sodium nitrate. Now, we can predict the formation of precipitates from reactions like these using solubility rules. And so go back to the previous look at solubility rules in the first video in this series, and you'll see how those can kind of come into play. So how did I know that silver chloride was going to be a precipitate? Well, I have to know my rule for chlorides, and that chlorides are usually soluble in water. However, silver is one of the exceptions to that rule, and therefore silver chloride is actually going to be an insoluble solid instead of a soluble one. Now, precipitation reactions we can often write using net ionic equations, and we'll get to more of that in just a minute. Again, the other type of primary reaction we can look at is an acid-base reaction. Acid-base reactions are sometimes referred to as neutralization reactions. And these are chemical reactions that take place when we have an acid reacting with a base. And when an acid and a base react with each other, we end up getting a solution of water and a salt of some kind. And again, the word salt here refers to any ionic compound, not just sodium chloride. And so the salt that gets formed in here is always going to have this composition. It's going to be made up of the cation of the base and the anion of the acid put together. And the hydrogen and the hydroxide are going to come together to make water, and that's the neutralization part. That's the part where the hydrogen and the hydroxide essentially cancel each other's effects. Now, in either case, one of the reasons we need to be extra careful with reactions in aqueous solution is because the environment's kind of unique. The fact that we don't have true molecules for anything that's electrolytic, the molecular equation isn't going to give us the full story of the reaction. In fact, it can be a little bit misleading. It can lead us to believe that things are happening when in fact they aren't. And so to get around that, we're going to use ionic equations to show how solutions can change when they are combined with each other. And these equations will let us know definitively, based upon their net result, whether there's actually a difference between the reactants and products. And if there is a difference between the reactants and products, then we know a reaction occurred. If there is no difference, then it's just the opposite. We know that no difference means no reaction. And that's an important distinction to make. So from this perspective, I can look at ionic equations. Now, to turn any molecular equation into an ionic equation, we have to follow a process. The first is we have to write the molecular equation. And I'm going to add one little piece here. We have to write the balanced molecular equation. Having a molecular equation is great, but if it's not balanced, the ionic equation has no chance of telling us anything useful. The second thing, we have to identify the reaction species by type. And so this is where that solubility rules in business is going to come into play. So if you are not proficient in your solubility rules, if you have not passed proficiency number 5 yet, you really need to get working on it, because that aspect is going to be really key to being able to do these ionic equations. So I need to be able to look at something and say, oh, that's an acid, that's a base, it's strong, it's weak, that's a soluble salt, that's an insoluble salt. For all the species that are strong electrolytes, we need to rewrite their formulas in ionic form. So anything that is a soluble salt, anything that is a strong acid, anything that is a strong base, those are the ones that need to be rewritten in ionic form. And so an example of this, sodium chloride would no longer be sodium chloride in the ionic equation. It would become sodium ion and chloride ion. Everything that is a reaction species, that is a weak electrolyte or a non-electrolyte, is written in its full molecular form. And so this would be any insoluble salt. This would be any weak acid. This would be any weak base. And not that you'll see many examples of this, but any non-electrolyte would also fit in here as well. So if you had sugar, if you had ethyl alcohol, something like that, those would fit into this category as well. Now, ionic equations kind of give us the whole story in terms of everything in its pure form of how it actually looks inside of the solution. Problem is they can be a little bit redundant. There are going to be parts of ionic equations that are going to be common on both sides. And those ions that are common on both sides, we call spectator ions. And a net ionic equation takes those spectator ions and tells them to take a hike, and gets rid of all of the spectator ions. And so the difference between an ionic equation and a net ionic equation is the removal of the spectator ions. And so how this is helpful to us is that it lets us know, okay, if a reaction actually occurs, there's going to be a difference. Some of the ions that were ions in the reactants will be something else in the products. And if they're not, if my reactants and my products are identical to each other, look exactly the same, then that's a really good sign that we know, okay, nothing actually happened here. There was no chemical reaction. Now, the best way to go about doing this is to do lots of examples. And so we're going to start with this example, and then I'll do a second video later with more examples to choose from. So in this one, we've got lead 2 nitrate reacting with sodium iodide to make sodium nitrate and lead 2 iodide. We can see it's already been balanced for us. What we need to do now is we need to go about the process of identifying each one of these by their category. So lead 2 nitrate, nitrate ions are always soluble. So this is a soluble salt. Sodium compounds are always soluble. So this is a soluble salt as well. Sodium and nitrate are put together here. So this is a soluble salt. Lead 2 iodide is usually soluble, but lead is one of those exceptions. So this is my insoluble salt here. Now my next step is to turn this into an ionic equation. And for the ionic equation, I'm going to need to break all of these things that are soluble into their parts. So that means I'm going to have lead ion, lead 2 plus. I'm going to have the nitrate ion, NO3 minus. And here's one of the most common places where people make mistakes. Subscripts and coefficients carry over. So subscripts in parentheses carry over to everything inside of the parentheses. So I have 2 nitrate ions. In the case of sodium iodide here, that coefficient is going to carry over to both the sodium ion and the iodide ion. And then on the product side, same thing here, 2 sodium ions and 2 nitrate ions. And my lead 2 iodide is insoluble, so I actually keep this molecular. So it'll stay PbI2. Now what I want you to notice is that I've highlighted in red here, these are the spectator ions. Notice that I have 2 nitrate ions on both sides of the reaction and 2 sodium ions on both sides of the reaction. So the sodium and the nitrate did not change at all as we went from reactant to product. And so to turn this into a net ionic equation, I'm going to remove those spectator ions and focus just on the parts that did change. So my lead ion, Pb plus 2, reacted with 2 iodide ions to make the insoluble solid lead 2 iodide. And that is my net ionic equation for this. So in order to go to the net ionic, I had to go through this ionic equation first. And to do that, I had to be able to identify each of these by their category of soluble, insoluble, acid, base, whatever. So that's going to be the end of this first video. In the next video, I will do some more examples of total and net ionic equations. I'll also link to some other videos to help you get more practice with those. But until then, have a good afternoon.